In the previous video, we concluded that the simple regression model explaining the duration of a driving assignment for Butler deliveries, given the distance covered, had an R-square of only 0.487. That did not seem that impressive, all things considered. In fact, it can be reasoned that there are other factors, other variables, that affect the duration of a driving assignment, such as the number of delivery stops being made, or how fast a driver sped along the route. Let's improve the regression model by including additional explanatory variables. A regression model using more than one explanatory variable is called a multiple regression model. And when such model is linear, then it is called a multiple linear regression model. A multiple linear regression model in its most generic form looks like this. It still includes the response variable on the left-hand side of the equation. It still has the intercept b0 and the product of the slope coefficient b1 times the original first variable x1. But then it also has additional terms, b2 times x2, b3 times x3, etc. Note how each term in the right-hand side equation is linear, with each coefficient being multiplied by the corresponding variable and all the terms being added together. Multiple regression analysis is a very powerful technique, but the results can be at times a little confusing to interpret. This has to do with the fact that as the number of explanatory variables increases, so does the mathematical complexity of the model. In simple regression analysis, we learned that we can visualize the line fit plot with a scatter plot, draw explanatory and response variables on the x and y axis, respectively, and the regression model as a line with a given intercept and slope. However, as we increase the number of explanatory variables to just 2, data visualization becomes more challenging, as now we have 3 axes to draw, 2 for the explanatory variables, and the third one for the response variable. And as the number of explanatory variables further increase to 3 or more, then we can't even describe the overall model graphically anymore, because as human beings, we can only comprehend 3 spatial dimensions. And yet, we need to understand precisely the interpretation of intercept and slope coefficients, one for each explanatory variable in the model, in order to draw business insight from our analysis. Let's begin by considering again the example of Butler deliveries, but this time let's switch to the worksheet labeled multiple. It contains in column A the same explanatory variable distance, considered in the simple regression example, and then in columns B and C, it also includes 2 more explanatory variables: the number of deliveries made during a driving assignment and the gas consumption expressed in gallons. The response variable, the duration of a driving assignment in hours, is now included in column D. Let's ignore column C for the time being, and let's build a multiple regression model with the regression tool in the data analysis toolpack by selecting the range D1 to D301 for the input Y range, our response variable, and range A1 to B301 for input X range, our explanatory variables. Let's also make sure that the label box is checked and that the output is placed by the default new worksheet. Finally, let's only select the residuals checkbox and uncheck, if needed, the boxes for the plots. I will explain later why. The output looks quite similar to the one we analyzed for the simple regression example, but there are a few differences. First, in the regression statistics table, the R-square has increased considerably, whereas the standard error has decreased. This is due to the fact that the number of deliveries variable has increased the explanatory power of the model, which now can explain almost 82% of the variation of the duration of a driving assignment. The better precision of the model has also made the residuals smaller, with a standard error of only 0.82 hours, down from 1.38 hours. This increase in precision is also reflected in the ANOVA table, where SSR, the sum of squares due to the regression, has increased, and correspondingly SSC, the sum of squares due to the residuals, have decreased. Note how SST, the total sum of squares, has not changed, because that does not depend on the set of explanatory variables. Correspondingly, with the introduction of the second explanatory variable, the degrees of freedom for the regression is now 2. The coefficients table has now a third row, the slope coefficient for the number of deliveries variable. That allows us to build a new regression model, which looks like this. We now have an additional term given by the product of the slope coefficient for the number of deliveries and the variable for the number of deliveries. There are also some considerable changes for the other coefficients. The intercept is now only 0.12 hours. The addition of the number of deliveries variable to the model has greatly helped explain the data, so that now it makes sense to interpret a driving assignment that is 0 miles long and with 0 deliveries being made to last only a few minutes. The slope coefficient for the distance has changed very little from the simple regression example, and the slope coefficient for the number of deliveries provide us with excellent insight on the duration of a single delivery during an assignment. But before we delve any deeper into the interpretation of slope coefficients, let's consider the following. In simple regression analysis, the model could be interpreted as a line on an XY plane. But what is now the geometrical interpretation of the model in a three-dimensional space? It turns out that if a line maps to a two-dimensional plane, then a plane must map to a three-dimensional space. In this three-dimensional depiction of the regression model for the Butler deliveries example, you can see how the regression plane is tilted with respect to both explanatory variables, the distance in miles and the number of deliveries. At each combination of the two explanatory variables, the model produces a prediction of the response variable, which is the duration in hours of the driving assignment. In the near left corner of the model, you can appreciate the interpretation of the intercept of 0.12 hours, which is the predicted duration of a driving assignment when the distance covered and the number of deliveries are both 0. To better understand the interpretation of the slope coefficients, let's consider a driving assignment consisting of distance covered of 65 miles and 5 deliveries to be made. If we plug those variables values into the regression model, we obtain a prediction duration of 7.93 hours, or more simply, of about 8 hours. To interpret the slope coefficients in multiple regression analysis, things get just a tad more complicated, because now we don't just have a single direction, up or down the regression line, as it was in a simple regression scenario. Now we have a whole lot of different directions to choose from when we move around the regression plane. But because each slope coefficient concerns itself with the effect on its corresponding explanatory variable, let's define two privileged directions. One along x1, the distance variable, and one along x2, the number of deliveries variable. Then, the distance slope coefficient, which has still units of hours per mile, can be interpreted as an increase of 0.067 hours in the duration of a driving assignment for a 1 mile increase in the distance covered during such driving assignment. However, that's such a small increase that it is hard to appreciate it in the graphical depiction of the model. So let's take advantage of the linearity of the model and consider a 30-mile increase in the distance covered during the driving assignment rather than just one. The corresponding increase in the duration of the driving assignment will be just 30 times as large, or in this case, about 2 hours. But because we are moving along the variable distance, the other variable, which is the number of deliveries, remains constant at 5, as you can clearly see from the model. So, the correct interpretation of the slope coefficient in multiple regression analysis becomes the change in the predicted response variable for a 1 unit increase in the explanatory variable while holding the other variables constant. Conversely, we can interpret the slope coefficient for the number of deliveries as an increase of 0.69 hours in the duration of a driving assignment for 1 additional delivery being made, while holding the distance covered constant. But if each delivery takes about 0.69 hours, it stands to reason that 3 more deliveries will take 3 times as much, or about 2 hours again. You can see the same effect on the total duration while moving along the variable axis number of deliveries. Remember that just as in the simple regression example, the data points appeared as a cloud of dots above and below the regression line, in this 2-variable regression example, the data points appear now as a 3-dimensional cloud of dots both above and below the regression plane. It is just that the tilt of the plane along both variable axes improves the fit between the data and the model, therefore reducing the overall size of the residuals. Let's now add to the model the gas consumption variable as well. Because we have now 4 variables in total, we cannot any longer visualize it graphically. But that's okay, because I've only needed this graphical expedient to illustrate the interpretation of slope coefficients in multiple regression analysis. From now on, we can just interpret the regression output knowing what really goes on mathematically in the model. Let's go back to the worksheet labeled multiple and run the regression tool again, this time modifying the input X range to A1 to C301, and run it. When we look at the new regression output, we realize that things have not really improved that much. The R-square and the standard error of the residuals are essentially unchanged. And the coefficient for intercept and distance have just increased slightly. Another change we have to make in multiple regression analysis is with how we deal with the plot of residuals. In the last video, we learned how to visualize the residuals and verify the assumption for the linearity of the model by creating a scatter plot of the residuals versus the explanatory variable. However, in multiple regression analysis, we can have several explanatory variables, and it would just not be that practical to create a scatter plot for each of them. The remedy is to plot the residuals versus the predicted response variable, which can be easily accomplished in Excel if you selected a checkbox for residual when you run the regression tool on the dataset. Simply scroll down the worksheet containing the regression output, past the regression tables, and select both columns B and C for predicted duration and residuals. Then, create a scatter plot. Make sure to properly label both axes for clarity of information. As you can see from the plot of residuals, the dots form a straight band hugging the zero line with no pattern or trend to deviate from a random cloud of flies on the windshield. This is important because we really have no other way in multiple regression analysis to verify the linear assumption made on the model. But let's go back again to the variable gas consumption, whose slope coefficient was found to be a negative 0.14. What are the units of the gas consumption slope coefficient? Remember that slope coefficients have rate units, and in order to balance the units on both sides of the regression equation, the units of the slope coefficient for gas consumption must therefore be hours per gallon. So the interpretation of the gas consumption slope coefficient would sound something like this. A decrease of 0.14 hours, or about 8 minutes, in the duration of a driving assignment for a 1 gallon increase in gas consumption while holding the distance covered and the number of deliveries constant. In conclusion, we can make a couple of important decisions about a model. First, because the model does not really increase in precision by adding the gas consumption variable, it turns out that we can just exclude it from the model and go back to the previous one, the one with just the distance covered during a driving assignment and the number of deliveries, as it was just as good and obviously simpler. Second, we could instruct the drivers of butler deliveries that wasting more gas has only a very marginal contribution to the assignment duration. A few minutes saved for a whole gallon of gas, that is just not worth it, because with increased speed, there are many bad things that could happen during a driving assignment. In the end, the reason why gas consumption does not significantly add to the precision of the model has to do with the fact that the information provided by gas consumption is already included in the variable distance. If you think about it, a longer driving assignment will use more gas anyway. So it is not that gas consumption is not an important variable. It is just that interpretation of the coefficient is the change in the duration of a trip for a 1 gallon increase in gas while holding the distance of a driving assignment fixed. And that is what does not help the drivers, burning more gas to cover the same distance. The regression model tells us this important fact very clearly. The mathematical marginalization of the variable gas consumption in the model, because its information is already embedded in the variable distance, is a phenomenon typical to multiple regression models that is called collinearity. Two or more explanatory variables are said to be collinear to each other when they are strongly related to each other, and essentially, they tell the same story. Mathematically speaking, the regression algorithm will marginalize from the model the variable that contributes little to explaining the variation of the response variable. To prove how distance and gas consumption are related to each other, try calculating the correlation coefficient between them. Enter the following formula in an empty cell in Excel. Correl for correlation, and then the two fields A2 to A301 and C2 to C301. The corresponding correlation coefficient is almost 0.96. Explanatory variables should only be weakly correlated to each other, because if they aren't, it means that one explanatory variable can explain the other one. In other words, collinear variables are not independent from each other. We should read the model of the weaker collinear variable and run the regression again, as we just did.